So I'm George Dochev. I'm the CTO, co-founder of LucidLink. I'm going to talk about the architecture behind that. You saw the demo. Before I get into how we've architected the system, I want to provide some context on a couple of different levels. Number one, what's wrong with NFS and SMB protocols as we know them, right? They've been serving us well for the past 20 plus years, maybe 30 years now. But these are protocols designed in the 80s for low latency, always connected LAN environments. They're not designed for the internet long distance connections that we use today. And these protocols work very well today, but again, they're very chatty in terms of many round trips for very simple file operations, especially around metadata operations. And that chattiness, this round trip serial calls that you have to make to the server back and forth over distance really slow things down to a crawl, right? And everybody who's tried to use a file server over the internet, over the ocean, for instance, they've seen that this really breaks down to a point where it's unworkable, right? Now, we have revisited this, and we have redesigned this from scratch to address the limitations of these high latency environments. And we do multiple things. We do various optimizations. We split the metadata and the data separately. We synchronize the metadata and we stream the data to improve the responsiveness of the system. And I'll talk a little bit more about that later. But that's the situation with NFS and SMB. Now, the industry's response, right, has been probably in two large categories, right? One is the file sync and share category of solutions, which we all know and love, and they do a great job. We're not trying to displace them. They're fantastic for user collaboration and typically for small data sets and small files. Now, what they do is the source of truth or the original replicas of those files are stored in the cloud in some form or another, and they continuously synchronize, or in other words, copy all the files to the local machine on the local disk. And then the local application or the end user consumes them off of the local disk. So that's why they're called file sync and share. So by virtue of doing that, they mitigate the effects of intermittent connections, low bandwidth connections, etc., right? Again, this model works really well for small data sets, right? Now, another category of solutions, somebody brought that question earlier. This is probably a good moment to answer how LucidLink differs from the cloud storage gateways. Now, cloud storage gateways address this problem differently. There is typically a physical or virtual appliance that sits in a branch office or in the cloud in some cases, and provides a NFS or SMB connection to the front, but then tiers into the cloud. Now, under the covers, they also synchronize between the cloud and the gateway device, or what do they call them? Filers, edge filers, whatever. But under the covers, they do the same thing. They continuously synchronize data between the filer and the cloud, right? However, these machines have much more capacity in terms of storage, compute, network capacity, so they can serve multiple clients at the same time. Now, LucidLink has approached this completely differently. Instead of continuously copying files back and forth and trying to synchronize these data sets, we actually stream on demand based on the application and its requests. In other words, we give you instant access to the entire data set, which can literally be into the petabyte range. But as you're running an application, and as the application requests data and writes data, is the point in time where we actually stream those bits and pieces that the application needs. So there's really no file synchronization. Now, what that gives us, it gives us, number one, the ability to access large data sets without the need to pre-hydrate the data locally before you can touch that data, right? And some of these use cases that we covered earlier depict how that's used in practice, right?
So one quick question, just because I know it comes up at times and it helps to level set in a lot of people's heads is, so you could have your PSTs and OSTs mounted in S3 and still be running your local Outlook and not having to fully rehydrate that thing down.
Absolutely, that is exactly right. In the demo that we're kind of rushing through a demo, but when we boot up a virtual machine, we obviously didn't bring in whatever the entire...
Oh, the VM part makes sense. VMs work and they're sensible. Outlook is not sensible. No one should have a 3 terabyte PST that they're constantly farming stuff to, but they do.
Correct.
And it's architecturally
But Outlook
horrible.
does not read the entire file into memory.
Exactly.
And as long as it doesn't do that, we won't do it, right?
Exactly.
Yeah.
So this concept, can you break down what, when I think of streaming, I think of Netflix streaming. I'm pulling down the bits as I need it.
Correct.
So from a CDN perspective, absolutely makes sense to pull down just the part of the video that I want to see, and I'm done. If I'm dealing with a file that needs consistency, or if I've written something to a file, let's say it's in a block, a data block that's 300 meg. And I have a 10 meg connection out to the internet, 50 meg connection, it doesn't matter. It takes seconds to minutes to commit that to disk at the far end. Mm-hmm. How do you guys handle this whole concept of latency in writing to files when I'm streaming the...
Fantastic question. I have a subsequent slide that covers that.
Okay.
If you may, yeah.
But streaming, I'm thinking of streaming, you're using streaming in the same definition as a Netflix.
So we use the term streaming because we had to come up with a term, it's direct remote access if you wish, right? But streaming is analogous to how your Netflix movie streams, except that we provide the same capability for general purpose file access, not just for videos. And also it's read-write access, not just read access, right? In fact, Netflix internally has a similar technology based on the blogs that we're reading, right? They've developed something similar because they had to. Yeah.
So how do you handle collision detection on a file?
In terms of conflicts and stuff? Yeah. Well, yeah, I also have a slide on that.
Hashtag file locking.
I have a question. So help me think through this. I open up a document in, let's say, Microsoft Teams, okay? And I open that document and I can choose to open it locally, right? I'm collaborating with my teammate who lives in Sydney, and it's a large file, okay? It's got some video embedded in a PowerPoint, for example. I'm making changes real time as he's making changes real time, right? Yeah. And that is some of the same exact things as what you're talking about here.
I'm not sure what the question is, but this is application specific. We cannot possibly resolve these semantic conflicts. This has to come from the application. We're a file system, okay? Mm-hmm. If you're making changes and I'm making changes to the same underlying file, the file system, being a general purpose solution, doesn't know how to reconcile these changes. This has to be built into the application itself. So in the example that you're giving, that would be provided by the Microsoft Word, right?
Okay, so, all right, so because this is the storage itself is doing some of the same things as far as synchronizing the users as what the application is also providing.
If you think about it in that logical way, there are similar aspects to how they interact. Mm-hmm. But with Word, for example, or PowerPoint, we support global locking. So if they then can handle, like when you lock something on a hard drive, then that will also effectively be supported on our file system. But you also mentioned the cloud aspect of Word and Excel, those kinds of applications. And of course, we don't have any way to talk to those.
Okay.
If that answers the question.
Yeah, I was
If
just
you're
trying
talking
to think through it from.
collaborative like scenarios like Google Docs, actively working. This is at the application level. This is not at the file system level. There's
Okay.
nothing we can do to address that.
Okay.
Right? But we have collaborative features in terms of global file locking that we mentioned earlier that address certain applications in the architecture, engineering, construction, and media and entertainment. Adobe products, Autodesk products, right? They do employ locking, right? And they have local versus global model, and they push those changes, right? So they lock the global file, which we actually provide the locking. They would reconcile the change internally because they know the semantics of the content of the file and know which changes to push, and then they unlock the file, and then someone else can do the same thing. That's how this is achieved in Revit, for instance.
We could actually, with other applications, maybe, let's say, Adobe, Photoshop, whatever, collaborate with those applications that would not typically be collaborative applications. So would that be a fair statement?
Adobe also provides locking. So for instance, I can open up a file, and if you try to open it while I'm changing it, Adobe will say, no, this file is currently locked.
Got
right?
it.
And you could
All
be
right.
sitting on the other side of the planet, right? So that's the extent to which a file system can address this issue, right? We're not going to give you Google Docs type of experience. That's, again, at the application level.
Because that's actually a real big problem is two people are accessing replica copies of the same file, and you open your copy and you're doing your work, and they open their copy and doing the work because there's no file locking, and then
Right.
you go to commit, and then who's the master? Well, who saved last? You're the master.
Yeah.
And that's a huge problem with collaborative work in CAD workloads and in Photoshop and video workloads.
Or it just writes two copies and like appends the name of your machine
Yeah.
so you can differentiate the two, but that's not really any better because
Yeah.
then it's like,
Then it's
okay,
to sync
somebody
that
has
copy,
to
and it's
open
like, wait,
those
which
and
is the
merge
real
them.
master?
Yeah.
And then they have to reconcile after the fact.
Yeah, that's why, the Microsoft applications are the ones build their collaboration inside the application and use something like, OneDrive or whatever to enable that real-time collaboration inside the document where both people can be working. But it's not a file system.
And that's recent.
Yeah.
That
Very
they've
recent.
introduced.
So the advantages that our solution brings, obviously streaming instead of syncing improves performance, addresses to some extent the egress question earlier, because instead of hydrating the entire data set, we'll only stream what is necessary. We also employ persistent on-disk caching, so we're not constantly pushing and pulling data, only what's needed when it's needed, right? So again, your typical working set, independent of the application, I can just generalize a bit and say your typical working set is not going to be the entire data volume. So you're not constantly moving large data sets back and forth, right? I said that this actually gives you instant access to large files and volumes. It obviates the need to deploy complex networking or virtual physical appliances that you then have to manage, etc., because this is provided as a service. We also provide uniform access from anywhere. The cloud gateway solutions work really well for branch offices that need to be connected, but it doesn't really work all that well if you have people roaming around, nobody's carrying a gateway, right, in their backpack. So this solution, giving you a uniform access from anywhere, in the office, on the go, etc., right, again, opens up for different use cases. We, as mentioned already a couple of times, and I'll continue to talk about this, end-to-end encryption, customers in possession of the keys. We don't see data or metadata. We allow you to host your files, your volume, wherever you want in any object storage. And so we give you complete control over data sovereignty requirements, GDPR, etc. Right? As a result of the fact that it's a software solution, it's a fraction of the cost, and we also have full OS support. So this is what we set out to build, a secure enterprise scale cloud service, which is based on a distributed file system. I want to point out that we're not just a translation layer between object and files, because you can't really do that in practice, right? This doesn't work in practice because the object storage semantics cannot be directly mapped to file system semantics. For instance, object storage in many cases is eventually consistent. Object storage is a flat namespace, so if I try to project it and I rename a folder, I'd be moving, and there is 1 million files in that folder, I'll be actually moving 1 million files, right? There's no random read-write access, etc., right? So we're not just a translation layer. We're a full-fledged distributed file system that actually uses the object storage the way a local file system would use a disk, in a way. We treat it as a block device that is elastic, that is highly durable, that is cost-effective, etc.
Do we get versioning and like volume shadow copy type of
we do
stuff
get
we can roll back to?
as well. Yeah.
Max,
And I'll show you how that's actually.
I'm going to ask a storage field day question. How large are the blocks that you're writing to these objects?
Yeah, so blocks are, we default to 256K, and that's configurable parameter at initialization time. So it's a global shared namespace with full file system semantics designed to give you high performance over distance specifically with the highest degree of security and privacy, works on any object storage, supports large volumes. Somebody asked a question about the scalability limits. Let me address this quickly here. Every system has certain scalability limits, obviously. Ours today supports the petabyte range, and up to 100 million files. We're going to extend that down the road, but that's just the parameters within which we work. There are a couple of other requirements around this that we architected the system around. We're going to support offline mode of operation where some of the data could be pinned locally, and other features that we just need to keep rolling here. So this is the basic solution. This is probably the most important diagram here. Our solution is comprised of 3 components. We have the LucidLink client, which is a piece of software that sits on the client device, not to be confused with an edge device. That could be any device, anywhere, cloud or local or whatever. And this is where all the intelligence is and the client. That's where we do data compression, encryption, on-disk caching, etc. We have the LucidLink service, which is the component that we typically run, and that's what we were spinning up during the demo. This LucidLink service is a very small component that provides metadata synchronization and other features like garbage collection, file locking, snapshotting, etc. And then, of course, we finally have the object store where all the data is housed in a bucket in a customer's account.
The part that I'm not seeing here is what's the database for the file system?
Right. So the database for the file system is running in the LucidLink service as well as on the client.
How much space, like you gave an example of 100 million files. So let's say I do have 100 million files. How big does that metadata database get?
Yeah. So it's typically about a gig per million files. So 100 million file space will have about 100 gig of metadata.
Does all of that metadata have to live on every client that uses the file space?
Great question. We are in the we're going to release at the end of the year an enhanced support where the metadata would not be entirely synchronized. Today, the solution, the way we initially decided to roll out, synchronize the entire metadata. Okay. However, that's not very practical when you go into these scales, obviously, because the metadata becomes a big data problem by itself. Right? And so as a result, we're going to be streaming not only the data, but the metadata as well. Okay? We're actively working on that.
Your previous slide said that you support all modern desktops and services.
Yeah, it's a euphemism for, I don't want to deal with Solaris back in the 80s, but yeah, we support Linux. Let me answer it. We support Linux 32 and 64-bit, all flavors. We support Windows 32 and 64-bit desktop and server operating systems. We support Mac OS at the moment. And like I said, we also run, we build a product against iOS and Android.
Does that go back to like Windows Server 2003, or is it like 2000? No,
2008 is, I believe, where we draw the line.
2008.
Yeah.
I mean, that's reasonable.
Does it not
there's-
work on
That
2000?
is my VMware lab.
There's plenty of people that are still running 2003.
My VMware
Yeah,
lab.
we're not asking for anything.
But if you ended at Server
Not saying they should be
2003,
running it.
then you also ended at Windows 7.
Yeah.
Windows 7 we do support because we have customers using it.
But that's your most recent
That's
version of Windows.
yeah, that's the
yeah.
floor. Windows 7. We don't go back.
Okay.
No Vista?
Given,
So disappointed.
ME.
given this is supposed to become your, say, primary store,
It's eight.
so I was just wondering that, if there are high transactional file system, so, thousands of files are created per second or something, or deleted even. Given that S3 lags a little bit in terms of consistency, how do you make sure that that also works
Yeah.
as intended?
Yeah.
Yeah.
Well, that's part of the design, and hopefully I can cover that. But it's a longer conversation. I'll try to cover some of that, right?
Right.
So a couple of quick things. I'm not going to dwell on this. Again, we already answered the question about all the platform support. On the back end, we support any S3 compliant object store, and we only use the absolute minimum set of operations. So as a result, we're pretty much compatible with every object storage that claims to be S3 compliant. As far as performance goes, that's a whole different story, right? And that's why we have a certification process. And we also support all the cloud vendors minus Azure because they're not S3 compliant. We're going to be rolling out Azure support at the end of the year. Now, a couple of, this is the consistency question, and I'll try to answer it here. So, as you guys know, distributed system design has been governed by the CAP theorem, right? The CAP theorem tells you you can have, out of the consistency, availability, and partition tolerance, out of those three very important properties in every distributed system, you get to choose only two. That's the reality of the world we live in, right? What the CAP theorem doesn't tell you is that those two properties are fixed in time. So you get to choose different properties at different times depending on the needs of the application. And that's what we've done here, and that's probably going to answer some of these lingering questions about how do you provide consistency and whatnot. So the first thing we're saying is we're relaxing the POSIX model and normally run in eventually consistent mode of operation and employ write-back caching. So somebody asks, well, I have 300 megabytes, but my connection might take minutes to push that up to the cloud. Correct. So we will write the data to disk and then acknowledge the request to the application, and then it will asynchronously push the data up to the cloud. That's the eventually consistent mode. And this is the default mode of operation, right? As it turns out, there are many, many, many use cases that don't really require strong consistency, okay? And by virtue of doing that, we've dramatically improved the user experience and the overall system performance, right? However, I want to point out that this eventually consistent mode should not be confused with the S3 eventual consistency, because in the S3 eventual consistency, you don't get read or write type of consistency. From the point of each individual node, every node lives in a consistent world. What you write, you can read back at any given point, right? Unlike S3, Amazon S3. However, right, that creates conflicts. You could, in theory, write to the same file by two people could write to the same file and create conflict. That creates the need for conflict resolution. At the moment, we employ a last write wins type of simplistic conflict resolution. The good thing is that we actually save each individual updates in each individual write, so we can do more sophisticated forms of conflict resolution down the road. The strongly consistent mode. Now, there are certain applications, especially these collaborative applications, that use file locking that cannot possibly run in an eventually consistent world, right? They have to see the data that was updated. And so in the presence of file locks, we fall back to a strongly consistent model at the expense of performance to some extent, right? So if an application like Autodesk Revit would lock a file, and then you do a bunch of updates, and then you unlock the file, all the data that is pushed to the cache will have to get flushed to the object store before we release the lock. So to guarantee that another node opening that file will always see the latest and greatest version of that file, right? So we switch dynamically between the two consistency modes. A couple of other things that we've done. We've actually designed our own actor-based C++ framework that allows us to write asynchronous, parallel, and lock-free code, which is a very powerful way of writing solutions in this space, right? We do parallel I/O compression and encryption. We utilize parallel TCP streams on the back end to account for these networks with large bandwidth delay product, high bandwidth, but also high latency type of networks, where in order to saturate the network, you really need to.
Do you detect the latency on the network to the service?
We don't detect the latency, but we should, right? Today, we do a sort of a more rudimentary approach. We start with a 64 IOs, if I'm not mistaken, or 64 TCP streams, and then based on latencies, we have a flow control mechanism to lower the number of active TCP streams, right? So to avoid congestion. Of course, we have a prefetching mechanism that also runs concurrently and analyzes multiple streams, etc. So,
Excuse me. So do you also have recommended settings for TCP/IP local settings on the client, like window size, everything else that would work best for those clients, or is that something that you try to control yourself?
we don't try to control TCP window size, to be honest with you. We haven't gotten to that level of control and sophistication, but that's probably not a bad idea. We use HTTPS protocol on top of TCP, so basically whatever you get out of your environment. But there's probably room for improvement there, right? For optimization. Yeah.
Can you do like a layered, this is a scenario that I'm thinking of, is a lot of people have their on-premises file server, Windows file server, and it sucks. And they're always running out of space. Where they could present up the drive letters as, like, we're just going to drop everything in S3. And then we're going to still present up those drive letters to the end users, and it's all going to passing through. Yeah, you're shaking your head because people are going to do that at times.
This is done by customers today.
Mm-hmm. Yeah, we do support that.
Yeah.
Like I said, you can have a file server, or your existing file server, right? And you can install the LucidLink client on the file server and then expose that file space through whatever, UNC share, drive letter, whatever.
And that way it minimizes the risk in some cases of number of clients you're installing. So long as the clients your end client or your end IoT device is able to talk to that file server, SMB, NFS, whatever it is, then they'll be handled on the back end. It's a way to kind of get around some of those problems.
I prefer
Right.
Stiff.
You're also not breaking all the links to people's applications where they've linked to the file server directly and the share name.
It's all the J drive or whatever.
That's right, yeah. Some of these applications, for instance, require a UNC path, and they just won't work any other way. So
Exactly.
There's legacy stuff that we have to do with.
So it's nice that that's supported and a way that it's just a native way of actually handling that.
Yeah.
Which is convenient.
A couple times we said, end-to-end security. Well, what does that really mean? Like, most cloud storage systems typically offer server-side encryption, right? So, and of course, in-transit encryption. You're going over an HTTPS encrypted channel. But what they don't do is they don't give you client-side encryption where the customer has the keys, right? And that's what we have done. We've taken a very serious approach. This is one of the basic architectural tenets, right? Is to make this a suitable solution for highly sensitive workloads, so that people actually, decision makers can, more easily move their data to the cloud without worrying about exposing that data, right? So the data is encrypted on the client device immediately, and as it enters our system, and remains encrypted in transit and at rest. And only the customer holds the encryption keys. So neither LucidLink nor the storage provider, whoever that happens to be, has access to the content. So as you may have noticed in our kind of a high-level diagram, there is no server, there's no cloud gateway, etc. Right? It's a serverless type of model. Eliminating the server, however, creates the need to keep the metadata somewhere. You can keep the metadata in the object store.
So you didn't get to the question of key management. How do we? Is that later on in this slide deck?
Why don't you ask the question, see if...
How do I do key management? Where are the keys stored? Like how they're stored? How are they changed? What happens if a key is? You guys mentioned that you can change keys on the fly. So what happens if a key is exposed and I need to change keys across 50,000 desktops? What does that look like?
Yeah.
We could skip ahead on
Or 5 desktops. I mean,
Or 5
it's hard.
desktops. Yeah, it's hard. It's hard. This is hard. That's not a.
Yeah, because theoretically, all you have to do is have one laptop go out of your possession, and then you figure your key is possibly compromised.
There you go.
So this is a hard problem. There's no solution. I can't answer all these questions now. The metadata itself is encrypted. We use AES 256 in GCM mode. Each file in each folder is encrypted with its own key and creates an encryption chain. So each folder encrypts the key of the files that are in the folder, and that creates that chain. Ultimately encrypted by the root key, right? Now, the way the system internally works is you're an end user. You were given access to subfolder 1 through your password. The password wraps the user's private RSA key. We unwrap that key. The subfolder key is wrapped with the user's public RSA key. And once we've unwrapped the private, it allows us to then open up subfolder 1 key and then go down that chain and gain access to.
Can I revoke Alice's key?
You can revoke Alice's key.
And not change anything else. Everything else stays the same, but I revoke Alice's key and we can reissue her key in the event her machine's
correct. If for some reason the entire system is exposed, like root keys are exposed, then there's not much you can do.
So
we allow you to rekey the S3 credentials. These are separate keys. I'm not talking about S3 credentials. These cannot be rekeyed on the fly. That would imply re-encrypting the entire file space. That could be petabytes.
So from a blast radius perspective, if a departmental person lost their laptop, other than the ACL, no, so it's not departmental, it's user level at that point. So any file access that user has access to, whoever lost that laptop, is physically like losing my laptop.
Yeah.
If I can get into the laptop, get the key, I have access to all that data because this is just open 443 to AWS.
Actually, you don't, because if you today, say on the laptop, the agent is running, all the data that is in the cache is also encrypted. And by virtue of logging out, I've lost access to this data. I'm going to have to re-log into my system. So I would need to know the password.
When you say log out, so if I get someone's laptop, unless the hard drive is encrypted, if I get somebody's laptop, I'm in the machine. Like that's so. What considerations, like, do you guys have best practices for recommending? We don't have to go to it in this section, but do you have best practices around securing in devices so I prevent, if I get your laptop and your hard drive isn't encrypted, I'm getting in and I'm getting into your company's data.
Yeah. So typically, what you want to do is when you log into a system, do not check that stay connected checkbox. The moment you log out, right?
And I enforce
you're going to have to, can enforce at the file system level. Not today, but that's a frequently requested feature. And we already have a general mechanism to enforce various initial parameters, let's say operational parameters. That could be and should be one of them, right?
Do you support two-factor authentication for the logins?
Not yet. We use our own custom login mechanism, but we're going to provide ADFS integration.
Okay, I was going to say, are you going to do federation?
For sure.
Are you going to support Azure Active Directory as well if you're going to do ADFS?
Yeah, I imagine we'll have to.
Okay.
I imagine we'll have to, So.
This is where we were.
Yeah, this is where we were. So real quick. So again, we have the split plane architecture where the metadata is stored in one location, the data is stored in the object store. The metadata is obviously all the file system hierarchies, file system names, attributes, all of this is encrypted, AOCLs, right? And then we have the actual data content. Now, the metadata is based on a distributed.
We got about 4 minutes left. Maybe see if there's any final questions
Okay.
for wrapping.
So it's going to be hard to cover all that. Yeah.
So
Okay. All right. So I'm going to just breeze through this, right?
or see if there's
The
questions.
metadata is, and I'll ask the question. Open up for questions. So we have a log-structured data model that allows us to maintain each and every version of each and every change. And this works around the eventual consistency of Amazon S3 and other object stores. But it also gives us free snapshots, right? It also gives us free versioning. So there are good properties of this model, and that's the log-structured data model that we use. I'm not going to go into details of how this is done. So just maybe a quick word on the LucidLink service. We run a discrete service. This is not multi-tenant, right? We run a discrete service per file space, or we use the term file space. It's a volume in the cloud. The file service, the LucidLink service can run anywhere. We also provide redundancy and high availability for it. We run it in 3 instances based on the RAF consensus. And that LucidLink service, like I said, performs garbage collection because of the log structure design that requires us to scrub data on the back end. We do global file locking, snapshot management, etc. And one other thing I want to point out, this is not this server. There is no server. This is a service that sits on the site. It's not on the data path. There's no traffic that flows through it. So it's not performance critical. That's why it could be run in the cloud without any performance implications. Again, I said that the LucidLink client is where all the intelligence is. This is where we do the compression, on-the-fly compression, encryption, prefetching, write-back caching, and finally data placement in the object store.
And the LucidLink service does not sit on the customer's VPC. That's in your own.
Correct.
Your own
Typically,
internal.
we provide that as a service because we can monitor it. We have alarming mechanism, phones are ringing, etc. So we look at various performance, criteria and various performance characteristics.
What's your uptime estimate?
But you could run it locally. Yeah, you could run that.
Well,
That's actually what I was going to follow up with.
Yeah, since
We have customers who just want to be off the grid and they want to run it locally, and they
the
do that.
SLA question is an interesting one because the local client has a local copy of the metadata. That isn't as big of a problem if you think about it because they can keep working. So even if there was an outage on the service,
Right.
should that happen, then even that wouldn't matter.
well, it doesn't mean you have a file access problem, but it means you can't do additional management tasks.
Well, you can't lock or something like that, right?
Yeah. So just a few words on where we're taking this technology. Obviously, it's sort of the first stage of this development, and we're going to work on providing multi-cloud support. In technical terms, that would be multi-bucket support, so that, like I said, the file space can be housed across multiple buckets. We can either provide tiering or replication, and this addresses various issues: economics, distance to data, additional data protection, an additional level of data durability. If you don't trust your the single cloud storage provider, you can put the data in 2 completely different systems, right? And the data durability goes up with that accordingly. We're going to be working on deduplication, pertinent feature for VM backups, obviously, where this comes into play. We're also going to provide a site cache mechanism where when you're in the local LAN, you can designate a machine with enough storage capacity that just use it as a site cache. So every client goes to the cache if there is one, and if there isn't, goes straight to the cloud, again to reduce egress charges and extraneous network traffic. And of course, mobile support is also frequently asked feature.